Alright guys, so our next unit coming up, we are discussing energy. Now, energy has a lot of different definitions. There's not really one definition that is better than others, but it's really a way that we can describe an object's state, whether it's a state of motion or what the object's doing or how it starts to move. One of the best and most common definitions that you see is energy is the capacity for doing work. So it describes an object's ability to do work, and we're going to discuss what work is in a moment. Now, in physics, we're going to look at kinetic energy and potential energy. We will discuss the conservation of energy, and we will look at that in collisions just like we did with momentum. And then we will look at the work energy principle. Now, energy also appears in multiple forms, meaning you can have your chemical energy, your mechanical energy. There are lots of different banks, I would say, to store your energy. And so energy has multiple units. In chemistry, you discuss calories. In physics, we'll use joules, but also if we look at energy in terms of work, then you can say Newton meters. So lots of different things to go along with energy here. But the main thing you need to know is energy is a way we can quantify, put a value with the current state of an object. So you should have seen a video already about work. Work is done on a system by an external force. Now, an external force, for example, would be a tension force or an applied force from like a person or something like that. Anything that is not within your system. So if I were to draw a free body diagram here, my system is this box and the ground. The person is not in my system. So when the person pulls the block, they are applying a force, an external force to the block. The person is outside of my system. Now, when the equation for work is force times distance. Now, this is the parallel component of the force. When we talked about torque, we talked about a perpendicular component. Here, work only matters if there is a force vector and a displacement vector. Now, those vectors can be in the same direction or opposite directions, but we are only concerned about the force that is on the plane with the displacement. So here we have an applied force at an angle. The only force actually doing any work or causing the horizontal acceleration is the horizontal force. So if I were to look at the work done on this object, I would first say the work equals that horizontal component, which would be the applied force magnitude times the cosine of that angle, F cosine theta, times the distance that it moves. So work is only done when you have an object being moved some distance. Now, if the horizontal component of the force and the displacement are in the same direction, whether it's an object is being pulled to the right or the left, then you have energy being added to your system. However, if you look at an object and for some reason it is moving, let's say an object was moving to the left, so we have a negative displacement, but the force applied to that object was to the right, so maybe we have a string or something causing it to stop eventually. If that force is to the right, then energy is being removed from our system. That would be our component force there. So all you need to know now is work is your force times displacement. Okay, graphically, work is the area under a force and time graph. We're going to look at that a little bit in class with one lab, but basically, if you have a force and time graph, this should absolutely be displacement. Okay, force and displacement graph. Because work equals your force times displacement, we will be looking at the area under the curve. Now, this equation only works if you have a constant force, but what if your force is not constant? Then we would have to look at this area, look at an integral. Here we have a constant force, some displacement, so finding the area is as easy as doing our length times our width. However, if we have a force and displacement graph that looks like this, where it looks like the force is increasing as our displacement increases, then we have to find the area using the area of a triangle, 1/2 base times height, to get our work. Now, work is a transfer of energy. It's a process of moving energy into or out of a system via external forces. So, all that means friction is not an external force, because in most cases you include the ground in your system. You include or the earth in your system, in which case the earth is providing your gravitational force. So when an object falls due to gravity, that is not work being done by gravity, because gravity is not an external force. It is within our system. An external force would just be like a tension or an applied force, something outside of our system. Now, there are multiple banks available for energy storage. So in physics, we just look at mechanical energy, and we will look at kinetic energy, which is your energy of motion, gravitational potential energy, which is energy that you have when you are up at some height, and elastic potential energy or spring potential energy. Those are used interchangeably. That is when you have a rubber band or a spring or any elastic material, a bouncy ball, anything that could have some elasticity to it, we will have what's described as elastic potential energy. And thermal energy. Now in physics, we use thermal energy as a dissipated energy. So basically an energy you lose from friction. When I first learned about energy in high school, in my high school physics class, they discussed friction as doing negative work on a system. Now, we teach it a little differently, because we treat friction as dissipating energy, and therefore we get a rise in thermal energy being heat. Now, this is not the same thermal energy that you looked at in chemistry as ETH, okay? This energy is Q being MC delta T. You may or may not remember that. We will not look at EPH, phase energy. We are not talking about micromolecules. We discuss the macro universe, so things on a grand scale. And we're not dealing with nuclear energy here. We're just going to deal with these types of energy. Now, kinetic energy. Kinetic energy, when you are moving, when an object is in motion, it has kinetic energy. So, because work is a transfer of energy, we're going to have work is equal to the change of energy of an object. So, I'm going to show you the derivation for to the value for kinetic energy. So, work is force times displacement, and of course we know that this force is a component force. Now, that's going to equal our change in energy, or I want to say specifically our change in kinetic energy. Assuming all of the other energies are staying constant, then work, a force, provides a change in motion. We know that. Forces cause acceleration. So, I can figure out what the equation for this term, where it comes from. So, force is given as mass times acceleration. So we know that is our change in kinetic energy. Now, acceleration is given as, let's see, well, we're going to have to do some rearranging here. Let me show you where it comes from. I need to find something there. Now, I'm going to solve for acceleration by using this equation.
Have your attention, please. Please dismiss the wrestling team. cheerleaders and the drum line at this time. Thank you.
There we go. Now, there's no special reason. I'm just showing you how we get the equation for kinetic energy. That's all I'm doing. We are going to use this equation, plug it right in here. So, m Vf squared minus Vi squared over 2 delta x, and I'm going to change d here to delta x, because that's the same thing, equals our delta k, k being kinetic energy. Now, if you notice, this delta x will cancel with this delta x. So we are left with 1/2 mv squared, Vf squared minus 1/2 mvi squared equals delta k. So therefore, our kinetic energy must be the quantity described by 1/2 mv squared. Now, kinetic energy here, this velocity, this is not the vector velocity. This is just the speed value, because of course when you square it, we will never have a negative kinetic energy. Mass cannot be negative, and a velocity squared cannot be negative. So you cannot have a negative kinetic energy. Now, let's look at gravitational potential energy, not elastic. Okay, gravitational potential energy, again, we know force times distance equals a change in energy. Now, gravitational potential energy is U sub g. So here, if we talk about the force that is lifting an object or changing an object's state of motion, it's the force of gravity. So we have mg.
This is just a reminder that when the bell rings to end third period, we will be forming send-off line from the gym entrance, down the mall hall, and then down the Hall of Fame towards the steps going to the field house. We'll be send-off for the wrestling team as they're heading to state championships this weekend, and then we'll be returning to fourth period class. Thank you.
Okay, so basically I changed delta x to hf minus hi, h being height of an object. G is our gravitational constant. Mg is how we find the weight, which is the force dealing with gravitational potential energy. So Ug equals mgh is how we quantify our gravitational potential energy. Now, if an object has a height, it has gravitational potential energy. All right? Let's go on.